So, welcome to the joint colloquium of TILOS and HCSI. Today, we're happy to have Tianyi visiting us from Columbia University. So, Professor Tianyi Ling is an assistant professor in the Department of Industrial Engineering and Operations Research at Columbia University. His research interests lie in generative models, optimization for machine learning, game theory, social and economic network, and optimal transport. He obtained his PhD in electrical engineering and computer science at UC Berkeley, advised by Mike Jordan, and was associated with the Berkeley Artificial Intelligence Research Group. From 23 to 2024, he was a postdoc researcher at the Laboratory for Information and Decision Systems at MIT. I'll skip through some of those experiences and leave the floor to Tianyi.
Sure. Hi, everyone. Thank you so much for having me here. And also thanks, Ian, for a very nice introduction. So today, I would like to talk about the preference alignment for large language models. So this is a joint work with my student, Peter Chen, and also my friends, Xi Chen from New York University and Wu Taoying from Alibaba. Okay. So let's start with the main message. So there is the standard pipeline for training larger models and as well as AI agents. It will be divided into 3 stages: pre-training, supervised fine-tuning, and post-training. So the focus of this talk would be post-training. So the key finding or the key motivation of our talk is to find that the standard approaches called the direct alignment methods, like the direct DPO, can behave very poorly on so-called the noisy preference data and yields the phenomenon called the likelihood displacement. And our key idea is to use different approaches for different data. For clean data, we still use the DPO or some other direct alignment methods. But for noisy data, we developed our new method called ComPO based on the comparison oracles. And we find that our approach could elevate this issue and improve the alignment performance. This is the roadmap for my talk. I will start with why post-training needs alignment. Then I will explain why DPO and other direct alignment methods will become fragile on noisy data. I propose my own new approach called ComPO and explain how it works and what kind of theoretical guarantee we can achieve. Finally, we conclude this talk. Okay? Okay, here comes the first part. Why post-training needs alignment? So this figure nicely captures the standard pipeline for training a useful AI agent or large language models. As I have emphasized before, we start with pre-training on the large-scale text corpora, and then use supervised fine-tuning to improve the large language model performance based on the human demonstrations. And then we still need to do post-training to align the larger models with human preference. And the focus of this talk is again post-training. Pre-training is designed for optimizing the next token completion. However, even after pre-training, the large language model may generate multiple continuation, which could be valid. For example, if we ask how to make pizza, what we expect is a direct answer, right? How can we do this? But the larger model may just simply add more context to this question, because the larger model thinks that you don't finish your question. That's not what we want. After pre-training, the supervised fine-tuning is basically so-called the instruction following based on the human demonstration. But it is still not fully aligned with human preference because we still have some other issues like the tone, like the safety, such that multiple answers could be correct, but humans will always prefer some over others, and we want a larger model to behave like humans. Here I gave the example, right? For tone, no, I can't, sorry, I cannot, but I appreciate the invitation. Both answers would be valid for larger models, but clearly the humans would like the second one. So after pre-training and SFT, we still do not have the larger model which are fully aligned with human preference. Then what we hope to do is so-called the post-training. Here I also give the diagram for the standard post-training scheme in practice. And the key to post-training is so-called the alignment. And the standard approach is called the reinforcement learning from human feedback. So let me move to this alignment, reinforcement learning from human feedback versus the direct alignment. So what do we do for reinforcement learning from human feedback? It's just a thing that we collect the preference data, which will be in the form of this triple thing. X is a question. Y plus is a preferred answer, and Y minus is a dispreferred answer. We use such preference data to train a reward model and then simply run reinforcement learning method like PPO and policy grading or policy grading. However, the direct alignment methods removes two heavy components of RLHF. It will not build the reward model based on the preference data and do reinforcement learning, but directly optimize the policy over the preference data by defining some specific loss function. That's the key difference. That's why DPO is also preferable by many companies because it's computationally easier and lighter. Here comes the basic scheme for the direct preference optimization. We still have the data, which would be expressed in this triple form, X, Y plus, and Y minus. But we don't construct the reward model or do reinforcement learning. What we do is basically define this loss function in one. And you can clearly see that this loss function is a kind of the expectation on some log sigma function of the relatively log likelihood. So the goal of the DPO is to maximize this relatively log likelihood such that we can get more probability for generating the preferred answer based on question and less probability, lower probability for generating the dispreferred answer for the dispreferred answer based on X. Okay, now we have explained what DPO is and why the post-training needs alignment. Do you have any questions so far? No? Okay. Now then I will move to the first key part of this talk, just explaining why the previous approach would behave poorly on so-called the noisy preference data. So first, what is the differences between clean data and the noisy data? As I have said before, so after supervised fine-tuning, the large language model has already known how to follow the instructions. The only thing between that we want is to just distinguish like the human preference. So the SFT model generates some reasonable answers, and the likelihood pi SFT, right, dot conditional on X, which is basically the probability of generating the answer based on the question X, has already provided a natural signal for the strength of the answer. I give simple examples for clean versus noisy data. In clean data, the question is very concrete, and we have clearly different answers. The question is very concrete, and we have clearly different answers. Right? What is the capital of China? The capital of China is Beijing, and the dispreferred answer is China is a country. So clearly, under SFT model, the probability of generating Y plus would be much larger than that of generating a dispreferred answer. However, if we ask some other questions like write a polite refusal to a dinner invitation, then these two answers could be both reasonable and very similar under the SFT model, because SFT model cannot distinguish this term. Humans may prefer Y plus over Y minus, but the SFT model cannot do this. So the probability would be very similar to each other. Now think about this. The DPO just optimizes the relatively log likelihood, right? The stress of signal is very important to DPO. So in the noisy data, the signal is rather weak, but DPO could treat it as a very strong signal. And this just leads to some problems.
One quick question.
Sure.
Why SST couldn't distinguish the later noisy data?
Okay. Because the noisy data, the differences between y plus and y minus is not just a thing that these answers do not be the solution to x. Yeah. The difference is the time, right? Yeah, the y plus is more polite.
Right. I guess the question is, are they both in the SFT data set?
That's a great question. In SFT supervised fine-tuning, we only use a human demonstration, meaning that we ask one question and give one good answer, right? So, of course, if you have y plus in the SFT training data, maybe it can distinguish this. But it's also very likely that you only have y minus, right? So SFT model only knows that what could be the good answer, what could be the answer. They cannot distinguish what answer would be better from the human perspective, right? For example, it has never seen y plus, so it will treat y plus as some kind of similar with y minus. That's why I put it here. So the probability will be similar to each other.
Presumably, you would have sort of both kinds of answers, and it's not clear from the count of the answers which one is correct.
Yes. That's why we need alignment in poster training, right? In SFT, we only know what answer could be right. Okay, good. Cool. Okay, when can DPO become fragile? The key quantity in DPO is the relatively log likelihood, and the DPO is developed to optimize, meaning that it maximizes the log likelihood rate. However, it could maximize this relatively log likelihood margin in the wrong way, right? The goal of the DPO is to think that it wants to encourage y plus, right, to look much, much better, right? However, increasing the margin could have two different ways. The first way is clearly that we increase the probability of 1 plus and decrease the probability of 1 minus. But we can also push down the probability of both y plus and y minus, right? But we significantly push down the probability of y minus. It's just like winning the race, but not running faster, but just making every others worse than before, right? And in practice, what would happen is that the DPO will reduce the probability of both y plus and y minus, but move the probability mass to some irrelevant answers. This is really bad for the safe alignment. Let me give you one simple example, right? Before DPO training, the SFT model already returns two answers, safe answers, right? They refuse to answer this question. They think that maybe this question is not very safe. However, after DPO training, the likelihood displacement occurs, right? The larger model starts to answer the questions and also give the good answers. This is really bad, right? So that's why I put it here. So it seems that DPO can improve the relative margin. The optimization is successful, but because the objective function is not good. So the absolute likelihood of the preferred answer may decrease. Okay. And connecting back to what we have discussed before is just the signals, right? The signals from the noisy data is quite weak. So if DPO treats this signal very strong and use it to optimize the policies, it will lead, right, the policy to some bad stuff. Okay. This clearly motivates some other approach. We still hope to convert the signals to optimizing policies, but it's basically how we can do that, right? How can we do that? Maybe we can define some other objective functions. But think about this. The type of our data is quite different from the statistical data. We do not just have x, y, right? The feature label. We have x, y plus, and y minus. How can we use one single objective function to increase the probability of y plus and decrease the probability of y minus? It's clearly a non-trivial task, right? We don't know what kind of objective function we can use. But the good thing is that maybe we can use some other approach, so-called the oracle-based approach. Okay. So here's a contribution of our work. So we first diagnose that the DPO can misbehave on the noisy preference data. And then we propose a comparison-based preference optimization method, saying that we don't explicitly define the objective function, but we use the comparison oracles to convert the signal to the useful information that can be used to optimize policy. And also we provide both theoretical guarantees and empirical evaluations. Okay, in one sentence, we give a new alignment method that utilizes the noisy preference pairs via comparison oracles. Okay. Here is our design principle. We use the SST model to divide the whole data into clean data and noisy data, right? So the clean data means the strong separation, we have the clear winner, and also DPO works quite well. Because now we already have a good approach. We don't need to do too much things for clean data. But we also have the noisy data, which just reveals the weak separation, similar answers, and DPO can be fragile. So we use ComPO for this noisy data. But before that, we use SFT model to distinguish them. So what is a comparison oracles? We don't define any objective functions, right? We don't define any objective functions. But we instead ask another question. When will be one model better than another model, right? If one model have the larger probability of generating the preferred answer than another model, and also have the lower probability of generating a dispreferred answer than another model. If we put these two things together, we see that this model will be better, right? This is also a very good signal, right? It's also like in competition. We do not assign the explicit numerical score to each option. We just compare them, right? Like what our human beings do. It would be much easier and more robust, right, than assigning the numerical score. So more explicitly, we see that we give one data, x, y plus, y minus. It is natural to regard the theta prime, which is a parameter, right, of one model. Because remember, our model is pi theta, right? Pi theta y conditional x. This is the probability of generating y conditional x. The only thing we need to do is to, right, optimize theta. And the theta prime is better than theta if it generates, it's more likely, right, to generate the preference, and also less likely to generate this preference. And we impose the signal called C pi 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 prime. If equation 2 holds, it would be -1, meaning that theta prime would be better, right? Otherwise, +1. Of course, I have some other questions. This thing that maybe it's not -1 +1. You can put -1 0 or things like this. What I can tell is that we try all of this approach, and they perform similar in practice. And this oracle is only one that we can prove theory. That's why we put it here. Okay.
Yeah, in practice, it seems to be giving away some of the magnitude information that's contained.
Yes, magnitude information, right? But it could be problematic in some sense, right? Here is the simplest signal. We just compare, right? It's very unlikely that we will make mistake. But however, this signal is weak, right? It's weak in some sense, in optimization sense, but it's robust and reliable. So the practical advantages are things that we still do not need the reward model, as kind of the DPO outperforms the RHF. But more importantly, now, we don't even need the objective function. We just use this oracle, right, these signals to develop our method. That's a great question. Yes, it should be, you can put +1 as variable or some other value. It doesn't mean. If it's -1, theta prime would be better than theta. If it's some other things, we cannot see anything. We cannot see anything. That's why I also comment on the design of these oracles. Still much room to improve. But at least for some naive construction, right, we don't see too much difference in our experiment. Question?
If one of the clauses hold a
That's also a great question. We don't know. We don't know. We haven't tried this, but maybe you can modify the oracle to compare this. But another thing is that I see you just want to check and to all, right? In some sense.
Let's say if for statement holds,
yeah,
you give it partial credit.
That's a great point. So of course you can modify this, but here, because our work is the first one to use this oracle, we put the strict requirement to sending the signal. Because this signal is already very, very weak from optimization perspective. That's why we say that we hope to, give the very strong signal. It's just a thing that pi prime will be better than theta. Then we just go along this direction. Okay?
Also, does this thresholding make optimization harder?
Yes, it makes optimization harder because if you have the explicit objective function, right, you can use a gradient. But now you don't have gradient because we don't have the explicit objective. It's even we don't have the function value. I will talk about later. I just see that from optimization perspective, this signal is very weak. But from human perspective or from data-driven perspective, this signal is very reliable and strong. Right? However, in DPO, because maybe we use the wrong objective function, even though you have the gradient information, maybe it leads to some problem, as I have explained before. Okay, good. Now, what is ComPO doing? I have to say that I really like this approach because it mimics the human behavior. The first step is to generate, is through the the perturbation Z1, Z2, Zn uniformly from the unit sphere. And then we just try a different approach, right? We want to update theta t, right? We hope to update theta t to theta t plus 1. And we have several candidates, right? So theta t plus RZ1, theta t plus RZ2, we just try different approach, explore, right? Explore. We explore different parameters, different actions. Then we compare. We see which exploration would be better than before, right? If it's -1, it's very good. We should do it, right? If it's 1, then we cannot see too much things, right? And then we use some clever way to aggregate the information, right? Because we have already know that some action may be good, some action may not be good. Yeah. So Professor Wang, your question is really good because now if we choose +1, that basically means that we will penalize, right? We will penalize those zeta t. But if we choose 0, basically means that we cannot say anything. We don't penalize. But okay, the performance, we don't see too much difference. So we use this. And the aggregation is based on the 1-bit comparison, compressive sensing. So that's why the ComPO looks like the derivative-free optimization specialized to the preference pairs. That's also the reason why I see that, from optimization perspectives, we just receive limited feedback. But it must be true. Okay. And here comes, oh, please. Can you speak?
Can you do something more clever than providing more sphere?
That's a great question. Yes. Yes, that's a great question. We think about this. If you have some domain knowledge, right? If you have some domain knowledge, you know that what kind of the human preference pairs would be drawn from the specific task, right? That basically means that you want your larger model to behave like humans in some specific domains. Of course, you can incorporate that domain knowledge in constructing this kind of so-called exploration regime, right? Like human beings, I agree with you, but here we just employ the naive approach.
I mean, it's the method would be right to look at the derivative of the two log-like functions and see if we restrict the space where they're aligned.
That's a great question. That's a great question. Basically, what you want to see is that can we use the DPO, right? So the DPO information, DPO structure to improve the ComPO.
Yeah.
Perfect. I agree with you, Dima. Very good question. There will be some follow-up papers, but we don't explore it here. Right. I agree with you. I totally agree with you. Yes. Okay. And here is the basic scheme. So we draw the randomization. Here we only use the unit sphere, and we get the comparison oracles. And what I want to say is that this is what we do to recover a sparse normalized direction by solving this optimization problem, right? We simply aggregate these signals. Yi is the binary signal. Zi is a perturbation. That's why I see that if Yi is 1, we will penalize Zi, right? Because we minimize the sum of this kind of stuff. And then we put the constraint is saying that this variable g should have the small L1 norm, and also it should be normalized, saying that L2 norm should be small. And then we have a decent direction that we should go. So we update theta t plus 1 using gt hat. Okay, so this is the formal scheme, or we call the basic scheme. Base. Sorry? L1 now? That's a great question. It's saying that, okay, intuitively, because we only have the binary oracles, right? We only have the binary oracles. So they just do not have too much information. So we have to compress, right? We have to compress, because if you just use the dense stuff, right, it may just give you some weird stuff, right? Yeah, that's why we need to use this compressed.
Many portions of the line, right? When you compress the, I don't see it divided portions, right? That's like a one and doing standard.
Yes, yes. I agree with you. It's a kind of compressing information. Here we use L1 now. We can have some other approaches to do that. We can have, in fact, in our practical scheme, we modify it because we cannot implement this approach for larger model alignment. Solving this optimization problem is extremely computationally heavy, right? Because the dimension of G could be like the billion, right? So you also have the question. Yeah, speak loud.
How many samples, how many contributions do you need to actually estimate the G rate?
That's also a very good question. So in fact, we collect information, right? 100 samples. We only use 100 samples to do that. And no. I think it's wrong. You see M, right? The perturbation, right? It's not the data sample perturbation. That's a great question. Okay, this really matters in our experiments because at the very beginning, we don't have too much computing sauce. That's why I only use 100 perturbation, right? We only use 100 perturbation, and it already improves the DPO, right? That basically means that the noisy preference data contains much valuable information, right? You don't need to perturb too much. You don't need to try too much. And then we find the promising performance. Then we talk to our industrial collaborators. Industrial collaborators say, oh, maybe we can give you more computing sauce. You can see how much you can even get improvement. You're right. Then we switch to like the 5,000 perturbations. It gives us very impressive performance. So you're right, yes. And also this is kind of the advantage of our approach because it can be parallel implemented, right? You can just do several perturbations in each cluster and then aggregate. The only thing we need to do is aggregation, right? Yeah. You can do the perturbation across the clusters computer. Any other questions? I will also talk about it later. Any other questions? No? Good. Yeah. Then we provide some theoretical guarantee. So under the standard smoothness condition and also so-called the sparse gradient structure, meaning that the compatible structure, meaning that there exists f, right? There exists a function f such that it will be compatible with this oracle. I agree that there may not be such f, but we prove some theoretical guarantee here. It's saying that assume that we have such function f. Our algorithm will converge to one epsilon stationary point of this function f. Of course, you can argue that we don't have such f, right? Maybe we have multiple objective function f, right? Then what will happen? Then it will be the follow-up work. Okay, at least we give some theoretical guarantee, from the optimization perspective, and we give the explicit convergence rate, high probability convergence rate for our algorithm. So this is kind of the analogs of the derivative-free optimization algorithms. How many samples? That's a good question. So for this basic scheme, at each iteration, only one sample. So the sample complexity would be equivalent to this iteration complexity. We do not do the mini-batch stuff. Of course, in experiments, we do mini-batch, but for theoretical proof, no, we don't need it. Okay? So the role of the theory here is not to capture every practical detail of Lagrange alignment, but just to see that our approach is a principal approach, right? Perturbation, evaluate, and aggregation. This should be the principal idea. Principal idea. Okay. What would be the practical scheme? Of course, the first step would be divide the whole data into clean and noisy data. Second step, okay, here's an interesting thing. First, we only perturb a small subset of parameters. We don't perturb all the parameters. We don't need to do this because this is kind of the fine tuning, right? The SFT model already knows how to generate the reasonable answer. The only thing we need to do is just align it with the human preference. We don't need to modify too many parameters. So we only perturb the small subset of parameters, mainly the output layer. Then we don't need L1, right? Because we only perturb the small subset of parameters, right? So we don't need the sparse constraint. So if we don't simply drop the sparse constraint, but still keep this kind of the L2 norm constraint, we have the closed form solution. This is very important because we cannot do this double loop algorithm for LLM alignment. We need the closed form solution. And we don't lose too much, right? Because the practical insights told us that we don't need to modify too many parameters. But of course, we still want to further impose the sparsity. That's why we also threshold GP hat and keep owning the significant entries. That means that even for the parameter perturbation for the output layer, the last layer, there still exist several small entries, and we simply cut them off. Okay. So the practical scheme is GPU friendly, since the oracle queries and aggregation over perturbations can be done in parallel across GPUs, right? Can be done. Thanks to this closed form solution. Thank you. Please.
You basically, for every perturbation you're running forward pass parallel, right?
Yes.
For every sample, now you have to run M additional runs compared to the DPO, right?
That's also a very good question. Yes, but if you have many GPU, yes, okay. But the interesting part is that memory issue. For GPU, you need a lot of memory, right? To store grid. However, for this, you don't.
Okay, so you're saying backwards a lot cheaper.
Yes. But I agree with you. For the computational stuff, like the running time, right, it's kind of the same, right? Because we have a lot of implement tricks in DPU. Good. Okay. Now I have 3 slides for the experimental results. The first slide just gives the core results in the winning rate. That basically means that the ComPO could improve DPO. We first run DPO over clean data and follow up by ComPO for the noisy data. And then it will just improve the reigning rate for the DPO purely with all the data sets. This is the first slide. The second slide is saying that if we have the ComPO, we significantly elevate the likelihood displacement. After ComPO on noisy data, our model indeed improved the probability of generating the preferred answer compared to the SFT model, and decrease the probability of the dispreferred answer compared to SFT model. This is very important to save alignment, right? The third slide is responding to your question. It's saying that the ComPO is practical refinement step for noisy data, and I have to say it's much better in this kind of memory stuff because we can just implement ComPO across several different GPUs. In fact, we implement ComPO over 30 A40, and we find that for each A40, right, the memory requirement is quite low. Okay, but we do not just see that ComPO replace DPO. It's complement to each other. We first run DPO and then followed by ComPO. Okay, so we do not directly compare ComPO to DPO. We just see that for different type of data, you should use different approaches and combine them. And ComPO is also computationally efficient, right, compared to DPO. Okay. So here, let me conclude this talk. So in fact, I'm an optimizer. I always want to connect some modern application problems to classical optimization ideas. And I feel that larger model alignment is a typical one. So now you can see that we have a practical pipeline leads to new optimization problem with completely different problem structure and a data structure. The data structure means that now you have the preference pairs, which will be different from the standard statistical data, and also different problem structure. And the path for our work is just to gain this practical insights, convert it to the spatial structure, meaning that we find that the comparison oracle might be suitable for extracting information from the noisy preference data. And then we develop the efficient algorithm, which could get the provable guarantees under some assumptions and also can be implemented across GPUs. So this exactly matches what our work have done. And also, this connection to optimization theory demonstrate how those essential ideas could be used. They are still very useful. We should not drop them because at Columbia, so many students complain that we take a lot of optimization classes, right? So we study the old application problem, right? What would be new, right? We want to study AI, want to study LLM. And our work is kind of the response to them. You have to sit there and study those classical optimization ideas, right? Because they will be useful. They will be very useful. If you don't know them, how can you develop the new algorithms to improve the performance of larger model alignment, right? So that's the end of my story. Thank you.